Everyone been paying attention today? So, heard all these interesting talks. Probably heard a lot of these sorts of things today, like event sourcing, command sourcing, CQRS. Who knows what these terms really mean? Who's confident to put their hands up and say they really know what these terms mean? It's kind of interesting. So when I was asked to come and do this, I just had a little look around to see what the current state of play is in this space. And on the web, just last week, there were some interesting tweets about this. Someone having a go at event sourcing where it claimed to have these things, but it didn't really work. And it was followed up by Kelly Summers pointing out, well, actually, I'll rewrite that tweet for you. I'll point out that some of the stuff isn't that easy and has a lot of problems. This one I found was actually one of the best. It's kind of small writing here for people at the back, but it's pointing out that event sourcing is actually quite difficult. It's hard. And one of the most common problems with it is the fact that we don't really have a common understanding as yet, because it's quite an early, quite a new thing that's out there. So I even went to some of the main sources and tried to compare. So if you read Martin Fowler's blogs, it's quite interesting, and they disagree with the documentation in EventStore itself. The EventStore documentation says that his blogs are actually talking about command sourcing whenever he's mentioning event sourcing. So I find that kind of interesting. I'm an old academic in how I approach things. So one of the things I did was, let's look for any research papers on this subject and see what I find. Well, I did a search and I found 3 references. 2 of them case studies, and 1 was this paper, actually from here in the Netherlands, which is kind of interesting. But it's sort of talking about the dark side of some of this, and it's kind of showing at this moment that it's still early. But is this good? Is this a bad thing? Well, what I'm going to talk about today is go back through a bit of the history of this and talk about events and logs and state machines and some of the stuff that's been around since the 1970s, 1980s that we're building on to get here. I get to build systems that are quite interesting in this space. Some of the highest volume systems in the world, like financial exchanges, reserve banks, telco systems, games and gambling online. It's kind of interesting. And these sorts of patterns get used a lot at this sort of level of scale. And when I talk about scale and quality that's in there, I'm talking things that are capable of doing millions of transactions per second with response times measured in the tens of microseconds. So it's kind of a bit more extreme than what most people look at. So when I talk about quality, I want to talk about those sorts of attributes and how they fit in with this and what we kind of do. So I want to start off and talk about state machines. Everyone's heard of state machines, I'm sure. How about Mealy and Moore, the state machines? Anybody heard those 2 terms? There's actually some interesting history here and different approaches. Well, Mealy's a kind of common one that we'll normally think about, Mealy state machines, and there's 2 functions we sort of think of. We think of a transform function where we've got a state of a system, we apply an input to it, and we get a new state. We also have output functions where we have a system that has a state, you apply an input, and you get an output. And this is pretty much common in how we look at state machines and how we approach them. Our programs often are effectively state machines, sometimes not expressed as clearly as a state machine can be. Where this gets really interesting for these type of systems at any sort of scale is we start looking at replicated state machines. And this is where we can have an ordered set of inputs. We apply deterministic execution, and that will give us the same state and same outputs at the end of the day. And from that, we can build really interesting things. Usually, we're talking about event logs. And for this, in my terminology, I'm looking at ordered inputs. Now, people will look at other ways of looking at this. So you'll get people talking about inputs, changes, outputs. I want to cover the stuff that has got significant research into it and things that have even been formally proven to be correct, and we'll explore some of this. But there's also something else I find in the domain that I work in. In many financial systems, you're not allowed to throw data away. We have to keep data for at least 7 years after we have finished trading with any given customer. So not even just while we're with them, we must keep it for 7 years afterwards. So throwing data away is generally a bad idea in this space. If you're the person who's legally responsible, the end result of that could be prison. And I've been the person in many companies who's been the legally responsible person, had to make sure we abided by the law. So I'm kind of aware of following this up and making sure it's done correctly. But there's other good reasons for this. Is like whenever you just throw data away, you can't go back and correct. You can't fix things from the past very easy. So I'm a big fan of recording the inputs, not so much the outputs, and I'll come back to it. Now, I know that many people who look at events or systems, they want to record outputs. And I'll touch on this later and why there's different ways of viewing this and different things we want to look at. But let's sort of build this up and go through it. So let's talk about domain models, because that's kind of the core of why we end up building systems like this. The event logs are interesting, but how we apply them to domain models. That thread that I mentioned had this interesting response in it. So Jessica Keir pointed out that some of those claims were false, but there's very good reasons why we want to do this. And one of the important reasons is how we can build models from this, and models that reflect complexities in the real world. Something that I've found that really stands out is building models that are free from the restriction of data stores. And that's where a lot of the power can come into these sorts of systems. If you're building a model and you're restricted by your database and some of the rules it imposes, and you often can't deal with the very rich and complex domains you're dealing with. And finance, this is very common in sort of order matching, risks models. Some of the interesting trading strategies are incredibly complex, rich models that are a pleasure to work with if you're free from the restrictions of data stores. And so that's why a lot of these systems tend to go that way. But as we build these sorts of systems, we have some things we have to consider. And as developers, we need to be aware of certain things when we're building certain types of systems, because some ways of building don't have restrictions. Other ways of building do have some different ones, and we just need to be a bit cognizant of that. One of the things that really stands out from this when you start building these is you must have algorithms that are deterministic, because if you're going to replay a log to get yourself back to the same state, you need to be dealing with deterministic algorithms. And sometimes this is a real surprise to people. The things that they think are deterministic are not deterministic, and you end up with nodes in the wrong state. One example of this is hash maps in Java. Are people aware that the iteration order of hash maps are not deterministic? In fact, they're deliberately randomized. I see people end up getting tripped up by these sorts of things all the time. So as you develop your algorithms, you need to be choosing things that are deterministic, otherwise you can't get back to the same state. Another thing that stands out, and this is a discipline I think people should have across all development, but you particularly have to have it for these type of systems. If you do not validate all of your inputs before you apply a mutation to your model, we don't have transaction rollbacks so easy when you're applying inputs to a system to go from one state to another state. If you have an exception in the middle of a number of steps of mutation, you end up with a problem that's very difficult to roll back and to make clean again. Where if you take the approach of validate all inputs that they're in their appropriate ranges, and then take action if they're not before you start mutating your model, you get a model that ends up being a lot more sound, and it ends up staying correct and hold those nice robust properties that we want to have. If you don't, you get bitten by that. As a network engineer, some of my background, I'm very aware of a thing called head-of-line blocking, which some people don't be aware of in applications. And head-of-line blocking is where a large job goes to go onto the network, a large packet or a large message. It shouldn't hold up everything behind it. It should be broken up into smaller chunks and fed in gradually. So you get fair utilization of the underlying resource. We see this in scheduling algorithms and all sorts of problems. But when people build these sort of systems, they often don't be aware of this. And so they run the big job that blocks everything until that job is complete. We can get around this. There's techniques of dealing with it. We will break down that job. We'll use timers to schedule the next phases of it. And I'll talk a bit more about timers later. And kind of lastly on one of these things is as we go over time, things change. We add stuff. We get really quite large, complex systems. As we get these complex systems, some things are running on different versions. And the only way we can cope with that is we need to version all of our communications, all of our ways of interaction. And when we extend something, these extensions must be optional with good defaults, because if something is receiving something that it doesn't yet support, it needs to be an optional thing for it to get. The defaults are important when it's the other way around. So which end has been upgraded first? You got to make sure that if you're sending something and you're sending it from an older version to a newer version, the newer version is going to get something that it doesn't have the data, it applies the default option. If it's the other way around, it's ignored, so it shouldn't need to be applied. And we have to build and move forward like this. So there's lots of really interesting subtleties in what we do with this. So we now have this model. We can build it up over time, and we build it up by applying all of these deltas, these events that are coming into it. We end up with how do we recover and recover fast? And the obvious thing that we do with that, and most people are aware, is you take a snapshot. And you take a snapshot of your current view of the state. If you want to reload and get back to the same state sooner, you take the latest snapshot and apply events from that point going forward. But how do we create snapshots, and how do we do it efficiently and deal with them over time? A common problem I see is people very often record more the implementation details of their model rather than the essence of the model. And you need to sort of distill your model into its canonical form and store that. Often that works really well if you do like an ER model of your object model, and that's what you'll end up storing and reconstituting from. So you're describing the entities itself, you're describing the relationships, but you're not saying this is done with a hash map, or this is done with a B tree, or this is done with something else. Those give you quality of service in the model that you use later on. But that's not what you should be storing in your snapshot, because if you want to migrate it, it's much easier if you're dealing with it in a canonical form. When you encode it, you also want that to be efficient and nice and compact to deal with it. So choosing your codec really starts to matter when you care about performance, and if you want to take these really often, so you can recover much faster if you're taking snapshots more frequently. But if you're taking them frequently and your model starts getting to be quite significant, you want it to be very efficient. So choose the codec that you encode your model up with. And some codecs are not just a few percentages faster or slower than each other. It gets into orders of magnitude. I work on some binary codecs where, like a financial market data message, we can encode them in about 15 to 19 nanoseconds per message. And that's in some of the codecs that we're using. I've seen other codecs that maybe you're going up to Google protocol buffers and it's taking nearly a microsecond. You're going to XML or JSON or some other formats and you're going into multiple microseconds to deal with it. It really restricts how much data you can get in your model. So you'll be looking at 3, sometimes 4 orders of magnitude difference in the codec that you choose and how you sort of package up your model. So you make these choices and you start dealing with them. And this gives you also faster recovery and faster propagation to other places. I'll mention versioning a number of times because we need to version everything if we want to move and live with these things over time. I've had to live with systems that have run for a few decades. And with that, you need to be versioning everything and make sure everything's got a version number on it, and versioning the code and tying everything together. Actually, the model for your system over time is an interesting model in its own right, and sort of be aware of that. If you don't build this versioning in, your migration and the longevity of this system will be cut to really slow you down. You need to think about this and deal with it. You need to be able to go back to a point in time, load a particular snapshot. What is the code that's associated with that snapshot? Do things like store the gate hash of the code that runs with that snapshot, and you do with it. Even better, can you take a model and develop an IR, an intermediate representation of that model that you can encode in binary and store with the model itself, so it describes the model. So have a meta model for the model stored with the model so you never go back with it. These are the sort of things you have to look at and think about. And we need to store them in a form that's easy to distribute. So if you just store it in a normal file system, how do you get it around? Do you have to put a web server over it? Do you use distributed file systems? Do you put them in places where it's easy to find and look up? It becomes important for how you approach that. And can you move that data quickly to another node if you need to and be able to react at some stage future down the line? So you have to start choosing these things carefully. mentioned time, and timers is a really interesting subject when we start dealing with these systems, because there's some rules to it. Sort of rule number one, if you're ever building these systems, is don't read the system clock. It's got a number of issues to why we don't want to do that. You won't get determinism across your nodes. You need to have an idea of time within a cluster. If you're going to replay a part of history, you need the concept of time to be stored with that. So rule number two, don't read the system clock. Try not to do this. It will come and bite you. You need to put a timestamp on every event that you take into your system, every message that you have, because this way we can start to associate when something happens. So make sure your data representation has the ability to encode the time with everything. And you need to be able to store time and time unit to know that things evolve over time. So 10 years ago in finance, everybody stored things with millisecond precision. We had legislation changes within Europe under MiFID II that you needed to have finer grain precision than that. So we needed to go to microseconds. Many people have gone to nanosecond precision on storing stuff. So you need to be able to do that and keep these things going over time. I think it's generally really important that whenever you store any units, you also store what those units are qualified in and keep these things together so we can deal with them over time. And when you have time dealt with in these sort of systems, how do you manage time? How do you then sort of set timers for the future? How do you make sure a time event has passed? And so you've got to build this all in. And you can do really interesting things like run tests and time travel in the future, time travel to the past, and see when things expire. You can run tests quite fast. I've had to build systems where we built our own timer wheels that we did similar things that the kernel typically does, but do it in an efficient way. Because you want to be able to register a timer and then cancel it again later. And that becomes a really common thing. So is it order one behavior to go and find the timer to cancel again? Most timers you'll find are canceled or rescheduled rather than ever expire. And you start to use them in quite a lot. Like one example where we'll end up using timers in a second is integration. Right? We build these really nice, beautiful systems. How do we fit them in with everything else? Because not everything is going to be an event source system. It will end up having to deal with databases, deal with traditional systems, deal with web systems, all sorts of things. That's natural. You need to put gateways in your design to adapt from one model to these other models. And the models is also including how things are integrated, how they work. Databases are a common thing you'll have to deal with. Relational databases in particular. How do we use them starts to get interesting. If you look at an RDBMS as a ledger, it's in an append-only data structure, it eventually becomes a log. You get a very similar way of thinking. You'll also use it incredibly efficiently. If you use the update statement, you end up with lock contention. You end up with lots of reformatting and restructuring of storage inside a relational database if you look at how it works under the hood. There's an interesting test for you on any projects. Don't give permission for the update statement to any SQL run as a user. Give select, give insert, but don't give the update. It really changes how you think about the model. And then what is, you're recording new facts. So if I live in an address, if I change address, I don't update my address. I put in a new address with a higher sequence number for a correlation ID or a timestamp for when and to. And what is my current address? Well, it's the one that's in the current date range or the one with the highest sequence number. It's a much better way of thinking. It also means that you don't end up losing data over time. And this is like a general thing of thinking about these systems. I keep coming back to is don't throw data away and don't mutate data because you lose history, you make mistakes, you can't fix it. Always add. And if you find you've added something incorrectly, well, add another record that takes it forward to the correct state again. This is how accountants work. This is how the real business world functions. Don't go mutating stuff. The excuse used to always be, but storage is expensive, so we'll mutate in place, and that way we keep storage compact. That argument doesn't wash anymore. Getting vast amounts of storage very cheaply is very easy, and then we can always go back and retrofit. Whenever we're going to integrate these things, they need a negotiate state at startup. So I have an event source system and it's run so far through its log and is dealing with a database that's further downstream. What if I'm replaying? How do I know what to put into that? Where have I put things in before? Well, give every insert that you have a change number, and you start off by looking up what change number has I got to. If I'm less than that change number for what was in my log, I won't actually insert it. If it's greater than that change number, I start inserting it again, and I can safely replay. I can deal with it. Things are working together, and I don't need distributed transactions. It becomes a much clearer way of working. And as we deal with these other systems, we're going to send out requests to them. We're often going to be expecting responses. This is one way where timers are very useful. Make everything asynchronous. Don't make it synchronous in how you interact with other systems, because as soon as you make it synchronous, you're now temporarily coupled. You want to decouple in space and time, and we deal with that by sending out a request and having a timer that we can retry later, or we can cancel or take some compensating action, and we register a timer to be able to do that. So a little bit of background that I've covered. What I'm much more interested in covering in this talk is the qualities of these systems. As part of the subtitle of this talk is, so when I'm talking about qualities, I'm talking about systems that need to run at millions of transactions a second, need to be very secure, need to be very reliable, like sort of 100% uptime or as close to it as possible. So very high numbers of nines. We're building and trying to function in a certain way. And people throw around this term a lot. Everyone familiar with non-functional requirements? Who likes this term? I detest this term. It's a real mistake in our industry. Like, let's look it up in the dictionary. Non-functional, having no function. Serving or performing no useful purpose. Generally, that's what this word means. And like, we shouldn't be using these words that way. Like, look at another thing. It's not performing or able to perform a regular function. So we're talking about requirements. We really want something that is useful. And so if you look at how architecture is moving at the moment, people do not use the term non-functional. They talk about the quality attributes of a system. And that's where a lot of these things are. So what's the performance? What's the security? What's the usability? What's the fault tolerance, reliability, robustness? All of these things. These are the qualities of something. We want something made with good quality. And the words matter. So think carefully. One of my real bugbears about our industry is we put terrible names on things. And often people don't even look up the name in the dictionary before they put it on something. Our industry is littered with this. Like non-functional is one example. One of my favorites is random access memory. Do we really want random access to memory? That wouldn't be very useful. I'll randomly give you something back. I want arbitrary access memory. But maybe it just didn't sound so good to give it that name. And don't get me started on software maintenance, because we don't grease oil and do maintenance on software that way. So what do we care about for some of these things? So fault tolerance. We want our systems to be able to tolerate a failure and continue giving good service. That is a good quality we want in one of these sorts of systems. I often see this debate. So I kind of go back 10, 20 years. If people were doing something for fault tolerance, they would typically sort of create a primary and a secondary for a system. So the primary would be running, it's backing up to a secondary that may be hot or may be cold. It may be synchronously replicating to it. It may be asynchronously replicating to it. And the idea being, if the primary dies, the secondary can take over, and there's usually some means of dealing with that. That is fraught with problems, and yet I still see people today trying to build systems like this. So you've got a primary secondary system. Let's try and automate it. You've got two nodes. Now, what happens if the secondary thinks the primary has failed? Should it automatically take over? That's usually where people start going with this. Well, what if you've got a net split and the primary is still functioning perfectly well, servicing customer requests, and the secondary goes, I can't talk to it anymore, so I'm going to now take over. Uh-oh, you now have got a split brain problem where you've got two nodes trying to deal with that. You may say, well, I'm going to manually take some action. I've been the person at 2 o'clock in the morning dealing with a dead primary system, trying to bring up the secondary, and I'm half asleep and I haven't had coffee, and I make mistakes and I run the wrong scripts and get things wrong. It's really not a good way to go with these things. And if you talk to a lawyer about this, when you say you've got a resilient system, what they really care about is repudiation of business transactions. So if you get a customer who comes in later and says, I did this, and you don't have a log to have that discussion with the customer and say whether they did or didn't do that, you're in a very difficult position. So if you've got a primary secondary system and your secondary has died or your primary's died and you continue processing and then you lose that node, you are not in any position to have a legal discussion with a customer to whether something happened or not, because you've no evidence of it either way. So primary secondary does not give you a good place to have non-repudiation at the end of something. Consensus is the answer to this. And this is where you have a majority of a cluster is still available to give an answer at a latent point. So simple example, if I have 3 nodes and I lose 1, I can still continue processing because I still have one other replica. If I lose another, I no longer have any ability to tolerate a fault and I should not be continuing at that point. Primary, secondary, you've already gone to the second stage. You need to have 3 nodes. And once you've got 3 or more nodes, you're into an interesting case of where you can now automatically elect a leader and do it with confidence because they can vote, and you can have a tie-breaking vote once you've got 3 nodes or more at that point. It becomes a way of resolving which is the right state to go with. And the work for this goes way back to the 1980s and even before that. So one of the fundamental steps forward was in 1984. Leslie Lamport wrote a paper on how we can use time rather than timeout in distributed systems. And this gave us some really interesting ways of doing replicated state machines. Later on, he produced Paxos as an algorithm. He was beaten to that by Barbara Liskov, who did ViewStamp replication based upon some of the same ideas. Also, simultaneously, Ken Berman was doing the work on virtual synchrony. So we had a lot of movement forward at the same time. This allowed us to have clusters of replicated state machines that were properly fault tolerant, where we could safely elect leaders and we could have clusters go forward, take the fault, and you would know you'd still have the majority of the cluster having the data so you could deal with that failure going forward and continue. Some of these were notoriously hard to deal with. Paxos has probably become the one that most people have heard of. It's actually notoriously difficult to implement and very easy to get it wrong. ViewStamp replication is easier, but it's still a difficult sort of subject. 2013, RAF was released, and the totally different goal for this was to come up with an algorithm where the primary goal was this is understandable and easy to deal with. And this kind of changed the world quite a bit around this, become incredibly popular, and most new systems are based upon RAF. When you read the paper, this paper is like 20 odd pages. It's relatively easy and most people can grasp it. Implementing it's more tricky. This paper is not a specification. It's missing quite a bit of detail. The PhD that backs it up by Diego is about 96 pages. It's got more detail, but still is not a specification. So there's still some work you've got to do around it. But the nice thing about Raft and some of these other approaches is they've been formally proven. In many cases, if you implement the model correctly, you can get certain guarantees. And for example, Raft provides you these 5 safety guarantees, which are really nice properties to have. We can have safe elections, knowing that the correct leader will be elected. The leader will append only to the logs, so we don't get any other problems with that. The logs will match across the leaders over time. We have leader completeness, so at any given point, the leader is guaranteed to have a complete history of that point, and we get safety in our state machines and how they operate. These are nice qualities to have in a system. It gives us certain confidence in that. But say, implementing this is kind of interesting. So you can implement it and you can get it to work fairly well, but is it particularly fast? Can you get high throughput, low latency? Some of the descriptions in this are alluding to it being done synchronously, and you don't tend to get that higher throughput in these things than how they work. It is possible to get quite high throughput by certain implementations, but let's look at it in a certain way. So let's say we've got a number of clients of a system, and we've got a 3-node cluster within that system. We will elect a leader using the protocol. The clients will then all talk to that leader. The leader will sequence the log. So now we've got a consistent view of the world. It will distribute that log to other members of the cluster. And then, based upon consensus, will allow the machines to progress forward, knowing that they can tolerate a failure of any one node in the system. If it was a cluster of 5, they could tolerate a failure of 2 nodes in the system and still continue processing. But it's a bit more complicated when you start making it asynchronous. Because whenever you get the data, you need to store it to disk, you need to replicate it to other nodes, you need to be processing it within your local state machines and moving forward in a way that's nice and safe. And if this is all done on the same thread and done synchronously, this is what slows it all down. We need to be able to go much faster than that. And we can go much faster by putting these things on different threads and breaking down the work asynchronously and doing it in a pipeline. But as a result, you get things in different positions over time. So the consensus modules replicating the state will have a view that's local to them of various things that they have seen and what they've heard elsewhere. So you'll have data on disk. So let's say these are messages or positions in a log that are coming in, and you're replicating those positions locally to disk. One will be faster than another at different points in time. Maybe one's taking a GC pause, one's ended up having to trim its local disk because the SSD is compacting. Various things can be going on. An interrupt happened on the machine that kept it busy doing something else. Amazon just decided to migrate your node, whatever it happens to be. So the logs end up in different positions. So the leader typically will be ahead of everything else because it's sequencing, but it's not guaranteed to be. It just typically will be. And so there we've got the leaders on position 29, one of the other services on 25, and others on 23, and that's for what it has appended to its local disk. Now the leader's getting reports back from all of the nodes in the cluster of what it has safely appended to its local disk, and it aggregates this and gets a view across the cluster for consensus. So it works out what is the position I can go given what's in the cluster if I was to lose any node in the cluster and still have a majority of that cluster. So in this case, what you're doing is you're taking all 3 positions and you're sorting them, and you're taking the top 2, and whatever the lower of the top 2 is, that's what you've safely got within the cluster. So the leader is saying that 25 is fine because it's got 29 locally. One of the other nodes has got 25 and one's got 23. So 25 is good. Anything 25 or lower, we can safely go forward with. It's distributing that information to the other nodes, including its own local service, which will end up dealing with that and processing. And then the services themselves will have their own position because if they're running asynchronously, they could be behind by various amounts on top of that. And so we've got all of these things happening in different orders. And then boom, you lose a node. You've got a bug, system crashes, Amazon steals your node, you've got a power failure, maybe the machine got attacked by a virus, who knows. Something happened and you've lost that node. We then elect a new leader within the cluster. And at this point, all of the traffic will go to that. Now this is fine, we can go forward from this point. So we're going to typically elect the leader that has got the most up-to-date view of the world, because this way we can go forward and we've got completeness around that. But what if that leader didn't burst into flames, didn't crash, it just took a horribly long GC pause, and then it came back again like a zombie, but it believes it's still the leader. This is where things get messy and difficult. You have to be able to cope with that and deal with it. So understanding what you have in all these different positions starts to matter, and managing that and dealing with it. Like if you're going to start dealing with anybody who says their system is fault tolerant, get someone in who knows how to review these systems properly, because very often what people say and what they claim is often not the case. And it's a very specialized task, but the whole thing of primary, secondary and stuff, I think these days are over. If we want to have a highly available system that's fault tolerant, it needs to be running some sort of consensus protocol, and it needs to be one that's been formally proven to be correct, and you've also got some assurity that the implementation is good on top of that. So we've got a reliable system. How do we make it fast? How do we get really good performance in our system? Well, kind of one of the first steps you want to do is don't pollute your business logic thread with other stuff. If you're going to the database, or you're going to disk, or you're going to network on your business logic thread, you've just stolen so many CPU cycles that you can't do other things. So you want to get everything off your business logic thread. And that includes also encoding and decoding messages in any inefficient format. If you're processing XML or JSON, then doing business logic, and then creating XML or JSON to send stuff out again, you've just wasted so many CPU cycles. That is a really common problem I see when I go and profile people's applications and they have a performance issue. So often you profile the whole thing and you'll see that all of this time is spent on various different things, and a couple of percentage points of your CPU time is done in business logic, and the rest is just wasted on all this infrastructure and layering and various ways we keep converting stuff. So get everything off your business logic thread except just the business logic. Then you can actually run at incredibly high transaction rates. And that's how things like financial exchanges and other sort of telcos, gaming systems work at the sort of rates that they achieve. A big part of that is also choosing the right data structures. Like, if there's one skill I think has stood with me over time more than anything else, I started programming in the 1980s, and everything I learned about data structures in the 1980s is still absolutely relevant today in 2020. It is not something that I've wasted any time on. Towards the end of the 90s and into the early 2000s, I got really good at web logic. I knew an awful lot about web logic. What a complete waste of my life. I'm never going to use that again. But yet everything I know about building a good object model, building a good relational model, building data structures, and I say not even just building data structures, choosing the right data structures is really the primary skill here that's important. It stays with you for life. Whenever you've got a model, you have relationships inside your model. Those relationships get implemented by data structures. And choosing the right ones makes a huge difference to the performance and the whole quality of the execution of that model. Whenever we do need to do something expensive, like expensive calculations, maybe we're going to disk, maybe we're going to the network, maybe we're doing something else, we want to amortize those expensive costs. If we all want to leave this building and go across into the city, the fastest way for an individual to do it is probably on a motorbike. If we all take that one motorbike backwards and forwards, it is not the fastest way to get us into the city. It's much better to get us all out onto a coach or a train and get us into the city. You want to amortize those costs and do it in batch. And we need to think about that in how we design our systems, not think in the minutiae of the individual movements. And it makes things much more efficient to think like that. And how do you actually get to know what matters and know where to focus? You need to make your development process so that you're continuously performance testing and profiling. Most people have no clue what the costs of some of the things are that they do because they just don't profile. Like, you talk about the red-green refactor cycle. I like red-green refactor debug profile. I do that all the time for everything I do. Why do I debug? Because whenever I'm running my tasks, I'll often stop them and walk them through in a debugger because it builds a really strong mental model, seeing your code being alive, seeing it operate rather than just statically seeing it. It gives you another pathway to see your code. It reinforces your view of your model, and profiling does the same as well. And you find really interesting things in profiles. The number of times I have seen exceptions being allocated in a profile, thinking, hang on, I didn't see any exceptions in the log. I didn't realize there's any errors happening in my code, but my profile is showing a significant cost allocating exceptions. And then I find that they have been allocated, they've been caught and silently dropped on the floor. And there was a big bug just hiding there that the profiler helped me find. So it's kind of interesting. Profiling is not just all about speed. There's other uses for it, and it's really good to run it regularly. So how do we scale this sort of stuff? We need to think about, I'm doing this in the small, how do I start dealing with it in the large? We'll start building separate services for each of your models. In finance, I often I'll have a model for risk, I'll have a model for order matching, I'll maybe have a model for portfolio management, a model for surveillance. These are all interesting individual models, they can be built off the same log, running on their own threads in their own ways. If you build them with the right sort of independence, you can also collapse them onto the same thread for testing or for a machine that doesn't have as much resource. But then you're just scheduling and slicing out the time for doing that. If even after doing that, you still got limitations, you need to be able to go faster, well, even an individual model, you can start sharding it. So everything typically comes down to people, stuff, and deals. Whenever you look at any model, there's only three major entities that really matter. It's usually people are trying to buy some stuff, and you do a deal to buy that stuff. And these things are, and so you can usually shard on one of those three dimensions through any model, and that allows you to scale. So shard by your customers, shard by your products, shard by the type of deals that you do, you'll be able to scale up in some ways. And then if we message between these services, if we do it all via the central log, we get a really good view across time. And it becomes incredibly powerful, this. I've been building these sorts of systems now since the early 1990s. And over time, I've started to become surprised at the behavioral changes I get in people. Most people who get used to this, they don't want to work in another way. Because some of the things that work out really nice is, someone calls up as a customer and says, I used your system yesterday at 3 o'clock and I had this problem and you've got a bug. Normally, if you're dealing with other systems, you're going around, okay, well, what happened? You're trying to scrabble together all sorts of bits of logs and bits of ways of working. With these sorts of systems, you go back to yesterday at 3 o'clock, you take the live logs from production from before 3 o'clock, play them through, looking for that customer's user ID, watch their order or their request come into a system, see what happened, and you can even step it through it in a debugger because you've got a completely deterministic replay of everything. It's so easy to go back and address customer issues, to deal with the bugs, to fix all those sorts of things. It makes life so much easier. I see people saying, well, okay, well, what if my read ratio is much higher than my write ratio? Well, we can use replicas for that, and you can query. So classic CQRS type things, but I usually try to caution people on this is because, yes, it's a cool thing to do, but it also has consequences. Can you read your own writes is an interesting thing in here. The whole eventual consistency issues that can come out from this. I actually seen one today on Twitter myself where I was trying to converse with someone and they wanted me to DM them. So I says, okay, I'll go to DM them. They say, okay, well, I don't follow you, so I'll follow you and then you can DM me. So they followed me. I couldn't send it for a while. It was like an hour later because that update didn't reflect through so quickly. It's a kind of clunky user experience. So only do that if you really have to. It's a kind of useful backstop technique, but don't rush to it. So I'm going to start wrapping up. Now, one of the things I have found more than anything over the years that actually really matters, models are really great and it's a lovely thing to do, but the fidelity between the model and the code is often where most of the problems happen. It's a really nice thing when people talk about ubiquitous language. The concepts that are in the domain are the concepts that actually end up in the code. That's one of the first great steps forward. But to keep your model up to date to reflect what's going on in the world and reflect your current understanding is such an important thing. And I find it's even more important when you work in the domain of infrastructure. So I build networking systems, I build transaction systems, databases, financial exchanges, these are things in the past where I'm not just dealing with a business, I'm dealing with a different domain. But getting that just correct, it's really important to focus on the model fidelity. And actually, if there's one area I think we could all improve in this space is have some way of cross-checking models to the code and keeping that in step because it really kind of matters. So kind of 10 plus years ago, when I co-founded LMAX and started working there, we built a financial exchange. We were the first financial exchange in Europe to get a license as an MTF on a broker, which is an exchange, and we could take customer coming in directly across the internet and manage their risk for them. We had to build everything from scratch because nothing existed at the time, and it was a real pain, but it was a fascinating time to do that. And I'd built these sort of systems before. A lot of what I've been talking about here now, you can do this here and now. It's a kind of interesting world. There is now options to do this that we didn't have before. And that's where I find that people coming into this, you don't need to be reinventing the wheel. There's actually some pretty good open source out there. I work on one of those projects. It's called Aeron, which lets you record messages. It's a fully functional messaging system, but we can record and replay messages at pretty much whatever speed of SSD you get. We can saturate any network, we can saturate any SSD, and we can do the clustering and stuff on that. And we've offered it out in open source because I want to kind of give back a little bit around like that, so I don't have to build all of this stuff again. In fact, I actually got fed up building the stuff for various clients in proprietary forms. And whenever we did this, the client that talked me into doing this, I says, okay, if I'm going to do it, I'm only going to do it one last time. And if I do that, I'll do it as open source. So some of the stuff is out there and available, and it's kind of cool that it is. And if I would give you anything to take away from this is, get involved in open source. So get your work out there, because it'll make it much better and of much higher quality than most of the other stuff you'll do internally. Just by the peer review. We're in a really weird industry whereby we do so much internally and keep it proprietary, and that way we don't see other examples, we don't get to learn, and we don't personally learn from it. Like if you were an architect who built buildings, other people come and see your buildings, they review it, they deal with it. If you're a surgeon, people get to see the results of that. We don't see a lot of what we do internally in software, and I think it's something that if we get better at it, we'll be in a much better place. So that's kind of it for me. Hopefully it's a little bit of a summary of sort of some of the stuff I've seen over the years in this space and some of the things I've learned. And if there's time, I'll take a few questions. Otherwise, you can grab me outside afterwards. And so thank you very much.